Okay, question number 4. In the frequency domain, controller design a lag compensator is used to improve the system's performance. Lag compensator basically it's used for the steady state response improvement. Lag compensator or a PI controller. Briefly describe the design steps to implement the lag compensator. Okay, so briefly obtain the value for k which satisfies the steady state. You will be given some steady state condition that improve your steady state error like this. So from this you will calculate your k. Okay, and then plot the corresponding Bode plot. Find the gain crossover frequency to obtain the designed phase margin, this gain crossover, and then determine the gain adjustment required for the system and find the ZC of for the compensation 0 of the controller, which is 1 decade below the gain crossover frequency, and then draw minus 20 dB per decade slope to determine your PC pole of the controller. Then put this formula as for the 0 S over ZC plus 1 S over PC plus 1, where ZC is greater than PC. So before proceeding further, let us first revise brief some concept that what is gain margin, what is phase margin. So this is a basic Bode plot. We have the log of omega on the x-axis or the frequency along the x-axis, and there are two graphs, one for the magnitude in dBs and the other one is the phase in degrees on the y-axis. So we plot these together. Okay, so first of all we see that when the gain becomes 0, for example here the gain is 0, so this is known as the gain crossover frequency. We call it gain crossover frequency. Similarly, when we will check when our phase will become minus 180, so here our phase, this is the minus 180, this is our phase is become minus 180, so this is phase crossover frequency. This one is phase crossover frequency, that one is gain crossover, and this is phase crossover. So these are the two frequencies which may be asked in the exam to determine gain crossover frequency and phase crossover frequency. Now gain margin and phase margin. So at gain crossover frequency you have to calculate the phase. Now phase, how will you calculate phase? This value minus this value, this will be your phase margin. The reference will be minus 180, so this is your phase margin. At gain crossover frequency you will get phi m, this is known as phase margin. Okay, similarly at phase crossover frequency, here you will have your gain margin. What is gain margin? This one minus this one, so this is your gain margin. So these are the four terms: gain crossover frequency, phase crossover frequency, phase margin, and gain margin. And gain margin, phase margin, these must both be positive for a stable system. This must have to be positive. Okay, so a closed loop system in the figure has the following open loop transfer. So the steps in the question 1 are explained here. This is the standard procedure also mentioned in the textbook, normal national textbook, and notes, that what are the steps. These are the steps. Okay, a closed loop system, the figure 4.a has the following open loop transfer function. So this is your open loop transfer function. So what is its type? By looking at this, its type, can you tell me its type? So this is a type 1 system, k over s into s plus 8 s plus 12. So its poles are at origin minus 8 and minus 12. This is our unity feedback system. We have a controller k, and the g of s is the plant transfer function. The corresponding Bode plot of the system when k is equal to 1 is depicted in the figure 4b and 4c. So these are the Bode plots 4b and 4c. This is 4b and this is 4c. So here we can see that what is our uh, this is our basically gain crossover frequency, because this is 0, approximately 0 dB, and here we have 0.01 radian per second. This is our gain crossover frequency, 0.01 radian per second. And minus 80, this is minus 180, and this one is your phase crossover frequency. It's bit little bit below the horizontal line, but it's 10. We can say 10, but actually it's more than somewhat 10 radians per second. So this is our phase crossover frequency, right? Okay, so next is gain margin and phase margin. We can calculate the gain margin and phase margin. Wait, please wait. Okay, the corresponding Bode plot. Using the gain adjustment technique in the frequency domain, GFS can be improved to yield a better response. Determine the gain margin, phase margin, gain crossover, and phase crossover. So gain crossover frequency, that we determine the gain, that was 0.01 radian, and phase crossover frequency is basically your 10 radian per second. So here these should be swapped. And what is the gain margin, phase margin? Here is the phase margin. At this gain crossover frequency, we will calculate the phase margin from 180. So this is our phase margin. Then you can calculate this, how much this should be, and it's in 90, exactly it's 90. So minus 90 minus 80. So like it will be like this, minus 90, sorry, minus into 180 minus 180. So it will be 180 minus 90, it will be 90. So this will be your phase margin. Okay, this will be your phase margin. Yes, it's right, 90 here. And what is your gain margin? Your gain margin will be at the phase crossover frequency, that is 10, and your reference is 0. So 0 dB, this is your reference, and 0, and this comes out to be here 50 to 70. This comes out to be something around 66 or 65 or 66. So it will be your 0, it will be your 0 minus into minus 65, that will be 65. So this will be your gain margin at the phase crossover frequency. So yes, it's written okay, 65 dB and 90 degree, and these values are swapped. Okay, so next part is determine the value of gain k from the Bode plots of the system, so that a phase margin of 60 degree is obtained. So you want a phase margin of 60 degree, hence determine the gain margin at this instance. So if you need a phase margin of 60, how will you get phase margin of 60? Phase margin of 60 minus 80. So you will have to place this curve at this point. So because minus 120 minus into minus 80, 180, it will become 60. So this is your 60. Currently it's 90, around 90, but you want 60. Okay, you want this to be 60. So to make the phase margin 60, you will have to go to the minus 120 point, and okay, but at this point minus 120, what is the frequency at minus 120? The frequency is so first you have to learn how to read this graph. This is 1 2 3 4 5 6 7 8 9 10. Okay, so this is basically at minus 120, you will be having the frequency which is more than 2 and less than 3, so it's around 2.5. Yes, we can say 2.5. It's also known as kV. This value is also kV. It's kV for, because it's a type 1 system. For the type 1 system, this value is basically kV. So this is also our kV. From kV we can get the steady state error, 1 over kV. If we take the inverse of this, we will get the steady state error, because ESS is equal to 1 over kV. So this is omega, which is also kV, that is equal to 2.5 radian per second. Okay, at this 2.5 radian per second, at 2.5 radian per second, at 2.5 radian per second. So see the magnitude. What's the magnitude here? 2.5 radian per second. It's around 2.5. It's here, right? It's here. It's I think it's minus 48. Yes, it's minus 48. So the gain is minus 48 at 2.5 radian per second. Here the gain is minus 48. Calculate from this, because this is minus 40 and every line is of 2, minus 2 dB. So this is minus 48 and minus 48 gain, minus 48 20. So okay, so this is the gain. Initial gain was 0, but you need a gain of minus 48 dB in order to make your phase margin 60. In order to obtain the phase margin of 60 degree, you need that much gain. So this minus 48, just take 20 log of k is equal to 48. This is the formula for this magnitude term. 20 log of k is the gain. 20 log of k is equal to 48, right? So divide 48 with the 20, that and then take its anti-log, 10 raised to the power 48 over 20. Basically it's 10 raised to the power 48 over 20. It will be like this, 251.19. so that is the gain. You need to operate the system at this gain in order to get this phase margin, the phase margin of 60 degree. You have to increase the gain up to this. You have to make your gain to 51.19. and what will be the again what will be the phase margin minus, this is not phase margin, again this is error, this is the gain margin. Basically initially it was minus 65 dB, and now you want to make it minus 48. So basically you are inserting an extra gain margin of 17 dB. So it's the gain margin of 17 dB you have to put extra. Okay, now we will do the third one is using k from 2. K is 251.19. Determine the steady state error. So I already told you that this is our kV, because both are approximately you can check is 2.5. It's 2.5, so our steady state error will be 1 over 2.5. okay, one way is this. Second way, you calculate from the formula k over s into s plus 8 s plus 12. So if we calculate here its steady state error, so kv is equal to limit s approaches to 0 s into g of s, right? Limit s approaches to 0 s into 251 over s into s plus, what was that, s into s plus 8 s plus 12 s plus 8 s plus 12. okay, so this s will be get cancelled. From this I'm just make this 251 divided by, put s 0 here, 8 plus 0 is 8 and 12 plus 0 is 12. So solve this, you will get some you will get kV, and after you get kV, your E infinity will be 1 over kV. for the type 1 system. So this is how you will get your steady state error. So here you can see that 1 over limit s into g of s 1 over 251.198 into 12, that is 0.382. okay, this is ESS, and your kV is 1 over ESS, that is 2.61. we approximate the this is we calculate 2.61, but from the Bode plots we got 2.5, which I told you it's also kV, so there is minor error, both are same, almost same. Okay, okay, now the next part is compare the value obtained with the static error constant obtained from the Bode plots of the system. Yes, it's almost same, 2.5 and 2.61, so the both are almost same. Okay, the fourth part is after a certain duration the original system is required to operate at a gain margin of 30 dB. Now first we change the phase margin, now we will operate it at a gain margin of 30 dB. Determine the corresponding gain K by applying the gain adjustment technique, hence the corresponding phase margin at this instant. So 30 dB you need a gain margin of 30 degrees. So phase crossover frequency, what is phase crossover? This is your phase crossover frequency, and here you need a 30 dB gain margin, you need a gain margin of 30 degree. First it is around, how much it is now, it is around 65. Yes, it's initially is 65, but you need 30, you need it 30 means you need it around here, this you needed almost 30, so you have to pull it up. So 65 minus 30, it is 35 dB. Your basically the gain adjustment will be 35 dB. 65 was the initial value, but you now need a 30 dB gain margin, so the difference will be 65 minus 30 is 35. You have to adjust the 35 dB, then you will get the 30 dB gain margin. So 20 log of k, that is equal to 35, that is 56.2, 56.23. so this is your gain which you will need to adjust. You have to adjust that much gain, then you will get the gain margin of 30 degree. And then at this point, while putting the phase margin, the initial margin, that is around 90 or 95, minus into minus 180, that will be 85. So this will be the phase margin at this position. So this is how this complex question gets solved. Okay, this is a question 4. Okay, the other questions are also same, so we do this on the same way because it's the part B. In the frequency domain controller design, compensators are used to improve a system performance. Describe the types of improvement available in actions. Again, this is again the compensator, the lead compensator, lag compensator, lead lag compensator. For the transient response you use a lead compensator, for steady state response you use a lag compensator, and you can also use both combined, which will become a PID controller. Okay, so these all explained in the slides and also here. Okay, improving the steady state error using lag compensation, we have to increase the phase margin to get the desired response. Improving the transient response using the lead compensator by increasing the phase margin, reduce the percentage overshoot, and increasing the gain, crossover, and bandwidth to realize a faster transient response. Improving both steady state error and transient response by combining both lead lag, which is the PID controller, gain adjustment to get the designed gain, designed overshoot and margin. Okay, so theoretical type question. Next part is B. Given uncompensated control system, this is the uncompensated control having a unity feedback with an open loop transfer function of the following form, which is g of s is 1 over s into s plus 60 s plus 90. So what is the type of the system? It's type 1. For this transfer function, determine the static error constant kv. Okay, kv, what will be kv? So we can calculate it quickly. Kv 1 over s plus 60 s plus 90. So what will be the kv? Kv will be limit S approaches to 0, S into g of s, limit s approaches to 0, s into 1 over s into s plus 60, s plus 90. So this s gets cancelled with this, and then put this s0, you will get 1 over 60 and 1 over 90. Okay, and your ESS or steady state or E infinity, it will be 1 over kV or 5400. This is your steady, it's huge, this steady state error is huge. Okay, so this is your steady state error, limit s into GS 1 over 1690, 1 over 1.85 times per minus 4, 1 over, this is the answer, and this is the steady state. This will be 1 over kV, that is 5400. Okay, so for the compensated system, kV is 11. kV is 11. How kV is 11? So for the transfer function, determine the static error constant kV, hence the steady state error of the system to a unit ramp input. This is completed. So C part is to improve the performance of the uncompensated system. Lag compensator needs to be, yes, you need a lag compensator for the steady state error remover. You need a lag compensator. The gain compensated Bode plots are shown in the figure. So these are the gain compensated Bode plots. Okay, here you can see that this is your 0 dB and this is your gain crossover frequency. That one is your gain crossover. It's 11. It's 11 radian per second, and that 11 radian per second is basically your kV, which I told already. It's basically kV. So kV is basically your this frequency. Okay, 11 kV is 11. Okay, this is kV and it is 11. It's compensated, that is not uncompensated, this is compensated system Bode plots. So it's 11, and how much compensation has been made? It's made, first it was 1.85 times by minus 4, now it's 11. So it's 11 over 1.85 minus 4, it's 5,009 sorry, it's 59,400 times. The value will be 400 times, 594,008, that times the value has been increased. So you have to take its 20 log of 594,000, that comes 95.48 dB. So that dB have been added in the system. That's why its steady state response has been increased, its steady state error has reduced and steady state response has improved. So the gain which is added is 95.48. Okay, so how 95.48 got? Because of this is the 11, this is your kV, and previous value was 1.85 times power minus 4. So 11 over 1.85 times power minus 4, it becomes 594,000, and then you have to take its 20 log, 20 into logarithm of this, you will get 95.48 dB. So the gain increased by gain is increased by 95.48 dB. Okay, next is design a lag compensator for the system in figure 5, question 5c1 and figure 5c2 with 20% overshoot and 100-fold means 100 times reduction in the steady state error obtained in 1. So here 20% overshoot. So for the 20% overshoot, with a 20% overshoot, what will be the zeta? Zeta you can calculate from the formula or from the your table if it is given in the exam. This is for the 20% overshoot. For 20% overshoot, your this is your basically around 0.5 something. So it's 0.5 0.44559 exactly. and this is your phase margin 66, that is 5 mm. This one is phase margin, that one because wait, this is 5 mm, that one, this is 5 tan inverse 2 zeta over minus 2 zeta. From percentage overshoot you got zeta, and from zeta you got phi m, and graphically it's you can calculate from here, from 0.45 or yeah, 0.45. So from 0.45 you are here now, so you can get its phase margin. It's around 40 to 50, in between 40 to 50. So this is the phase margin. It's 62. Here's the return 62. How is 62? It is 62 like this. Well, but I think it's better. So let's suppose it's 62. Okay, this is your phase margin. Basically the formula is this: phi m tan inverse 2 zeta over minus 2 zeta square. This is the formula, you get the phi m. So you need to verify this. I doubt this value is bit changed. Okay, next is okay. So 20% overshoot and 100-fold reduction in the steady state error obtained in 1. So steady state error 100 times reduction. So steady state error is 1 over kV. So if you multiply kV with 100, your steady state error will be reduced by 100 times. So your new kV will be 100 into your previous k, that is 11, right? If you multiply this with 100, your steady state error will be reduced 100 times. So this will become 1100. Your kV is 1100. So the new gain added to achieve kV is 59400. That was previous, it was raised, now just multiplied with the 100. This will be the new. And for the angle, this angle is this angle, I doubt this angle, but you have to add certain margin in it, that is 10%, 10 degree margin. Add a 10 degree margin, and this will be your phase angle around 72.87. just verify this, and this will conclude our this design. Okay, 20% overshoot, 100-fold reduction to steady state error. Design a lag compensator for this. Okay, so check at minus 107. So what is, how did you get minus 107? 180 minus this angle 72.87. by adding 10 degree margin in this, you will get 72.87, and then from 180 minus this, you will get minus 107.26. so this you have to check at this degree, minus 107.26. so let us check at here. So minus 107, how minus 1707 is obtained? By subtracting this from 180. This value minus 180, it will give you like this, minus 107.26. so minus 170.26 is somewhat around here. Yes, it's around this one, this value 10. so here omega is 10 radian per second, and at 10 radian per second, how much is the gain? Can calculate the gain at 10 radian per second of this compensation system. That gain is 5, approximately 5. Yes, because it's yes, it's approximately it's 5. so this, at 10 your gain is 5 dB, and your frequency is 10 radian per second. So the standard procedure for the lag compensator is high break frequency. High break frequency is 1 decade below. 1 decade below means 10 by 10, that is 1 radian per second. 1 decade below 10 times below. So 1 radian per second, this will be the high break frequency, and it is a standard method. Break frequency is 10 radian per second, gain is 5. High break frequency for the compensator is 1 decade below the gain crossover frequency. So 1 decade below is 10 over 10, 1 radian per second, and it starts with minus 5 dB at 1 radian per second, and then drop minus 20 dB per second until 0 dB, from 1 radian per second to 0 dB, and it hit 0 dB at 0.6 radian per second. So this will be the lower break frequency. Okay, the draw a minus 20 dB per decade back until it meets the 0 dB, and this is your lower break frequency point for the compensator. This is your PC. First one, your ZC. So your ZC was 1 and your PC is 0.6, and then put in the formula here. This is the formula, ZC over PC, put it here, and then you will get this answer, 0.6 into S plus 1 over S plus 0.6. So this is the design of lag compensator using your frequency response techniques, using your Bode plots. It's a bit complex, but with the lots of practice you will be fine-tuned to it. You will be doing this very easily. Okay, so next question, I think it's finished. Next question is question 6. The performance of the control system could be improved by using an appropriate compensator in the frequency domain approach. Two types of commonly used compensators are the lead compensator and lag compensator. This is again theory question. Lead compensator is used for the transient response improvement. Lag compensator is used for the steady state response improvement. And if you combine both, your both targets are achieved, and it will become a lead lag compensator or a PID controller, right? So refer to question 5, same question. Okay, an automated control system is given by the following open loop transfer function 4k over s into s plus 2. Again, it's again type 1 system. The polyplot of the system for k is equal to 1 is shown in figure. Design a lead compensator for the given system with the following specifications. So since it's a type 1, it's kV. kV is 20 per second. So if it's 20, what will be the steady state error? It will be 1 over 20. So here you can see that kV 20, and your steady state error, you can calculate the k from this k. So this is 4k over s into s plus 2. So kV is equal to 20 is equal to limit s approaches to 0 k over s into s plus 2. So 20 equal to this is your s multiplied with s cancels, so that is equal to k over 2. K over 2, wait, yes, kV is 20, 4k is also 4k, so it's basically your kV will become 10. Yes, kV will become 10. So yes, this is your k. So this is your k. K will become 10. K. This your k. This that one k. Your that k. This k is 10 basically for this kV 20. So k is equal to 10. Okay. Your phase margin of at least 50 degree. You need a phase margin of at least 50 degree. Phase margin for the, if the phase margin is 15 degree, you can get the zeta for this phase margin. Phase margin of 50, this is 50, the phase margin will be somewhat here. This is your phase margin, and this is your formula. You can get directly from the formula or from this graph. So the phase margin is, your zeta is 0.48, and from zeta you can calculate percentage overshoot. Okay, and this comes out to be 18%. Your percentage overshoot is 18%. So this, from phase margin you calculated zeta, and from zeta you calculated percentage overshoot. And gain margin of at least 10 dB, this is your gain margin you need, that is 10 dBs. And here these are the compensated system. So here you can see its values. In lead component on the given Bode plot solution is shown in this. Lead component of the given with the following specification. Right. Now minus 180. This is minus 180, and what is the your gain crossover frequency? That is your gain crossover frequency right here. This is your gain crossover frequency. So here you can see that at 0 dB, this is your gain crossover frequency, that is around in between 1 and 2. Okay, between 1 and this 0 dB, and again for this you have this value approximately is minus 1. So your current phase margin is minus 180 into minus 130 into minus 180, that is around 50. So the phase margin of the system, uncompensated system, is 50. Your uncompensated phase margin is 50 now, and the required phase margin for the compensator, what will be the required phase margin? Basically minimum it will be 50 minus 50, it's already 50, so 50 minus 50 plus 10, this is the marginal value, plus 10, so it will be minimum 20, and maximum it is 50 plus 50 plus 10, it should be your 110 here. So that is your minimum phase margin and maximum phase margin. Next you will have to carry on the design steps as given in the lecture notes.